Hello and welcome to this video on polymers. This is going to be quite a lengthy video because I am going to go through all the different condensation polymers and then some unique examples of them, as well as additional polymers. So you might get to a point where you need to pause or stop, take a break, come back, because it is going to be quite long. I'm going to go through a bit of the content. I've tried to condense that as much as I can, and then at the end I'll go through some exam questions. So when we're looking at condensation polymers, really there's two main types. You have your polyesters, and like the name suggests, you're going to have an ester linkage within those, and then you have your polyamides. And again, like the name suggests, you have an amide linkage in those polymers. Now within polyesters, we do have a unique example of polylactic acid, which does have an ester linkage, but it's specifically to do with the monomer lactic acid. And then with polyamides, we do have proteins, which do have those amide links, but often we see them also called peptide bonds or peptide links. Okay, so we could use amide peptide interchangeably because in the end, when we look at the link or the bond, they are the same. And then when we look at additional polymers, these are probably the ones you're most familiar with. You would have done quite a bit in GCSE, and that involves your double bond. Okay, so these will have your alkenes. And then the double bond breaks so that you can have an expanding chain. So if we start with those condensation polymers, looking at the polyesters first, and then that example of polylactic acid, and then we'll look at polyamides, go into proteins, and I'll be touching on amino acids for a little bit before I go into how those proteins form or what the linkage looks like in proteins. And then we'll touch on addition polymers and then those exam questions that I talked about. Okay, so these are our condensation polymers. Now you do need to know the definition of this. So this is monomers bond to form the polymer and a small molecule. And often that small molecule is H2O, and it can also be HCl. So that's a dash or HCl. Okay, so the important part in that is that you are specifying or using that word monomer in the definition, because monomers are bonding to form your polymer, and then you also, the definition needs the fact that you're forming a small molecule like water or hydrochloric or hydrogen chloride as well. Okay, so our polyesters. To form a polyester, if you think back to when esters form, we look at this here. Esters form when a carboxylic acid reacts with an alcohol, and that's how we get that ester linkage. So our monomers in this example, you're going to have an alcohol group, and you're going to have a carboxylic acid group, and often you have a diol, so two alcohol functional groups, reacting with a dicarboxylic acid. So if I show some generic monomers, so that's our carboxylic acid functional group, and then we can have any sort of chain there, and then the other end you will have another carboxylic acid, so dicarboxylic acid, and that's reacting with your diol. So you have your alcohol group, any sort of length chain, and then on the other end your alcohol group. So when these combined and we get our ester link, let's use a different color, see what happens. Just like forming the ester, that OH from the carboxylic acid will leave and react with that hydrogen from the alcohol, and that's where we're getting our small molecule H2O. Okay, and that's going to happen on either end. Okay, so this will leave, that will leave. Obviously we can have another H2O forming between that and that. Okay, so if we look at what our repeating unit would be, then you have your OH that's left, so we have our chain that expands there, our polymer chain that expands there, our middle part of our monomer, so your alkyl group, your R alkyl group or side chain, and then this carbon is now going to bind to that oxygen, and then we have that R group, the O, and that H has left, so we're left with the chain expanding there as well. So that we have N, because it can repeat N number of times, and that is our single repeating unit. That's okay. So what you just need to recognize is sometimes your carboxylic acid, your dicarboxylic acid isn't drawn linearly like that. So you might have to change around the molecule a little bit so that you can see where the chains are going to continue. And same goes for your diol. Okay, so if we look at that example, polylactic acid, so specifically looking at monomer. Actually, if I know I erased the repeating unit, but in this instance you would have two monomers. So two monomers joining together to make that one polymer. With polylactic acid, you actually only have the one monomer. Okay, so this is looking at polylactic acid. Okay, where the monomer is lactic acid. In lactic acid, you have on one end your alcohol functional group, and at your other end you have your carboxylic acid. So we have that single monomer. It's still that's going to come off, and that. So our single repeating unit will be the O, and then that carbon with the hydrogen and the CH3. Okay, so that's our single repeating unit. Often with something like this, when you only have one monomer forming the polymer, they're probably going to ask you for two repeating units. So if we look at modifying this to what it would look like with two repeating units, so change that, so it's two repeating units. This carboxylic acid will end up binding to that oxygen of another lactic acid molecule. So we would have an O, the C, the H, CH3, and then C double bond to O. And then it could continue. So that's our 2 repeating units. So you do just have to be mindful when they're asking for the 2 repeating units, it's because they are looking that you know how to show that ester link. Okay, it's very, very important that you do have that ester link shown in your drawing. Sometimes those are just dotted lines. So sometimes if you're going through the mark scheme, you'll see them as dotted lines. It's same thing, it's fine. How to draw them? Okay, I like to do them as solid lines. All right, so that's our lactic acid. So if we go on to our polyamides, then showing the amide link. Okay, so polyamides. So this is where you're going to still have, if we have our 2 monomers, you're going to have your carboxylic acid, sorry, your dicarboxylic acid, and I'm just going to show a generic one here so that our group saying it could be any sort of chain in the middle. Okay, so dicarboxylic acid. Now instead of an alcohol, we have a diamine. So you have your H2, your nitrogen, any length carbon chain there, and then your amine functional group on the other side. Okay, so this, we have our 2 different monomers, and if we show the amide link that ends up forming, if I change this to show those 2 hydrogens, in this we have the OH from the carboxylic acid that will leave and bind with a hydrogen from the amine, and that's where we're going to get H2O, our small molecule forming. So the link, actually same thing, that will go, and if I change those, one of those will go, and that just helps us to see what our repeating unit's going to look like. So imagine that gone, we then have carbon with an oxygen double bond, our chain that's in the middle, carbon double bond to an oxygen. That carbon's now going to bind to the nitrogen. That nitrogen still has a hydrogen, our carbon chain, any length, nitrogen, hydrogen, and then that is where our chain continues, and that can be any length. So that's our single repeating unit. And then the amide bond that you're going to look to recognize, that's your amide bond or amide link. Okay, your nitrogen bound to a carbon that's double bonded to an oxygen. Okay, I'm going to go through proteins, but I am going to come back to this amide bond or amide link and discuss the hydrolysis of the amide link, because the hydrolysis is different depending on the conditions. So acidic hydrolysis or acid hydrolysis versus base hydrolysis. So I am going to come back to that amide link to show the 2 different scenarios that we get when breaking that bond through hydrolysis. So proteins. Proteins form with an amide link, and they form from amino acids. So if we look at amino acids first, and then go back to our proteins. So amino acids. Now amino acids do behave differently depending on the conditions they exist in. So if we start by looking at just a generic amino acid. so carboxylic functional group with a carbon, some sort of side chain. That is what varies from one amino acid to another. The rest is always the same. And then we have an amine group. Okay, so that is our kind of generic amino acid. And then when I said that they behave differently depending on the conditions, we're really thinking about pH in this scenario. So we have something called an isoelectric point. Okay, and when the amino acid is at their isoelectric point, it is going to have no charge. So it's in conditions at the IP point, there's no overall charge. Okay, and that is because something called a Zwitter ion forms. Okay, and I'm going to go through what a Zwitter ion is, because I'm going to go through all the different conditions. So what happens when it's below the pH is below its isoelectric point, when it's at its isoelectric point, and above. Okay, so let's take a look at those. So if the pH less than the isoelectric point, I'm just going to make a note here, IP equals isoelectric point. All right. So at this condition, we are going to have a shift to kind of minimize that lower pH. And what ends up happening is we end up with an NH3 plus group. So we end up with a +1 ion when our pH is below the isoelectric point. And the isoelectric points vary from one amino acid to another, so you should be given that sort of information in a test, and then they would give you a pH and you'd have to draw the molecule based on the pH and the isoelectric point. Okay, well now if the pH is at the isoelectric point, this is when I said there's going to be no overall charge. So what happens, so we have our OH minus, and we end up with our NH3 plus. Okay, so yes, we have charges, but the +1 cancels out the -1, so overall there is no charge. Sorry, I'm just gonna adjust that so it's visible. All right, and the last scenario, when the pH is greater than the isoelectric point, and hopefully we can start seeing the pattern of what might happen. We end up with a negative charge. There we go. Okay. Now I talked about a Zwitter ion. This here, when you have the two different charges on that one molecule, that is what our Zwitter ion is. Okay. So oh, you can't even see. Let's write it here. This is, if I erase that, this is our Zwitter ion. Okay, where we have the negative and the positive charge, so the two different charges resulting in our no overall charge. That's our zwitterion, and it happens at our pH when it's at the isoelectric point. All right, so now let's look at our amino acids forming an amide bond or a peptide bond. Okay. So this is where, yes, proteins are polymers, and they are actually condensation polymers because you do produce water when they're forming. Because you can see that it's going to leave, and one of those hydrogens. So we do form water. You don't necessarily get repeating units because we have so many different amino acids, and each of them, you can have 3 amino acids and then a totally new amino acid and then your repeating units can vary. So unless they say it's a dipeptide and they give you the specific amino acids to use, your proteins vary from one to another because of the different amino acids and different amino acid combinations that you can get. Hopefully that wasn't too confusing. But if we look at the generic formation, we have that group, carbon with it, the R group, this nitrogen, which would bond to that carbon of another amino acid. And that is something of what they're going to be looking for, where this would be one amino acid like glycine, and that would be another amino acid like alanine, and then you've shown your amide bond here, and it is actually okay to call that a peptide bond. In biology you would call it peptide, in chemistry because it actually, you have your nitrogen carbon double bond to an oxygen, it is an amide bond as well, but they are both correct. All right, so now if we talk about, actually we'll use an amino acid as an example and look at the acid hydrolysis versus base hydrolysis. Okay, so I'm going to erase just so I have space. I'm going to redraw this higher up. And I am just going to make it generic. In the exam questions that I have, we'll look at some specific examples, but right now, there we go. Okay, so let's start first. If that undergoes acid hydrolysis, so it's going to act on the amide link, okay, and we're going to get that link breaking. Okay, so if I momentarily show that it's going to be breaking here, okay, because we once had a carboxylic acid there and an amine there, that's what we're going to go back to. So this monomer we'll get our OH. The R group hasn't changed. Now, because these are acidic conditions, what ends up happening is we get your nitrogen and we get 3 hydrogens bonding, so we get a positive charge there. Okay, and we'd end up having 2 of those, so that would also form we'll go back to its original monomer, but the amine, you'll end up having the 3 hydrogens with the +1 charge. Okay, now basic conditions, so base hydrolysis, we're still breaking up the polymer at the amide link. Okay, we're going back to the original, so there we go. And now, because these are acid conditions, we get your amine, but the OH, or the carboxylic acid, the C double bond to O, and then that alcohol group, we actually don't get the hydrogen binding. You end up having something like that. Okay, you get your OH minus. Okay, so it is worth taking note of the 2 different hydrolysis that you can have. Okay, well, taking note, you do need to know them, because if they ask for acid hydrolysis, you need to know that's the product, and if it's base hydrolysis, you need to know that's the product. Okay, and obviously the R group would be specific to the exam question they give you. Okay. All right, so that's it for condensation polymers. So if we take a quick look at addition polymers, and then we'll get to those exam questions. All right. So actually, if I start by showing a repeating unit, something like this, we're going to work a little bit backwards. We'll go to the monomer. Now, hopefully, you've noticed we have carbon with 2 hydrogens, carbon, hydrogen, and a benzene ring, and then it actually just repeats itself. So what I've drawn there is actually 2 repeating units, and this is polyphenol ethene. Okay, so let's look at what 1 repeating unit would be. So that would be 1 repeating unit. That was a bit sloppy. Let's try that again. Our chain continuing there. And then the phenyl group. And then the chain would continue there. So that's a single repeating unit. And then from there, we can figure out, or you potentially could have figured it out from up there, but we can figure out what would the monomer be. Okay, so it would have once, polymer would once have had a double bond, and we're told that here it's ethene. So 2 carbons, a double bond between those carbons. So basically this goes in, and that electron there would go in, and we end up between those 2 carbons getting a double bond formed. Hydrogen, 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 and the phenyl group. Oh, you want yours to be much clearer than that. 1, 2, 3, 4, 5, 6. There we go. All right. Not much more to say about addition polymers other than you need to know how to go from a monomer to a single repeating unit or to 2 repeating units. You need to be able to go from 2 repeating units to maybe the monomer or to a single repeating unit. So you need to, given one, you need to figure out any one of the others of those. Okay. You do need to know uses of polymers. I didn't go into that here because it's quite easy for you to look up yourselves, but just make sure that you are going in to your polymer uses. Okay, so exam questions. So remember with exam questions, you do want to be able to do your mind map, bringing it up again, because we're getting really close to your exams now. June, so 2-3 weeks away. I'm sure you're studying hard. You probably have already had some exams maybe, but still working towards memorizing this mind map if you don't already have it. I mean, you don't have to memorize it, it's one method, but as long as you have a method to be memorizing these reactions, because there are a few questions that I am going to be referring to them. All right, so if we look at this first exam question, I'm sure it is quite small for you to see, so I'm going to read it out. So this question is about the preparation, properties, and uses of lactic acid. Polylactic acid, or PLA, is used to make dissolvable stitches for holding wounds together. PLA breaks down into smaller molecules after 1 or 2 weeks. Draw the structure of 1 repeating unit of PLA. So they've actually drawn this lactic acid molecule a little bit different than what I have. But regardless, you should recognize you have here your carboxylic acid functional group, and down here is where you have your alcohol functional group. So that's where we're going to have the continuation of our chain, where that OH from the carboxylic acid will end up binding with the hydrogen from that alcohol. So if we look at, we'll have to turn this around a little bit. We're going to have our O. Continue on, we have that C then, that carbon. That carbon has a hydrogen. It also has a CH3. Please make sure your bonds are drawn clearly. Okay, and then we have this carbon, which will have a double bond to the oxygen, and because that OH group comes off, that's where we have our repeating. Okay, so that is our repeating unit for PLA. Okay, now the next part of this question, explain how PLA breaks down and why the stitches dissolve. In your answer, you should include the appropriate technical terms spelled correctly, so they are going to be checking you on your spelling there. So, technical terms. First off, we need to recognize that this is an ester link. So we need to talk about that. Okay, and if the PLA is breaking down, we need to talk about, well, what's happening to that ester link. And for an ester link to break, remember that's a condensation polymer, so we removed water in the formation of the polymer. So to break the link, we need to add the water, so it's hydrolysis. So your ester link for the breakdown is hydrolyzed. So they're going to be looking for ester link, or ester at least spelled correctly, and hydrolyzed spelled correctly. Right, and then answering the why did the stitches dissolve. So the ester link is hydrolyzed, and the monomer that forms, which is lactic acid, making sure you're spelling monomer correctly, that monomer is soluble. Okay, so when something dissolves, it's because it's soluble, and you should explain why it's soluble. It's soluble as it forms, it forms a hydrogen bond with the water. There we go. All right, so hopefully that wasn't too bad, and potentially you even paused it and tried it on your own, and then you can check your answers. All right, so that is one specifically to do with lactic acid and our ester link. So the next question, it's not quite a polymer, but it still relates to what we're talking about. So here, quite useful to identify your functional groups.